Welcome to another AI paper podcast. Today we're looking at a paper that really re-architects how AI agents handle long-term memory. We're talking about EverMemOS, a self-organizing memory operating system for structured long-horizon reasoning.
Yeah, and the problem they're tackling here is, well, it's a big one. When you use an LLM as a long-term agent, like a personal assistant over months or years, you hit two huge walls.
The context window is the obvious one.
That's the first, yeah. But the second one is actually more important. These agents rely on these fragmented, separate memory records. They just can't connect the dots over time or, spot when new information contradicts old information.
So it's like the system remembers a bunch of individual facts, but it can't build a coherent picture of you as a user.
Exactly. So EverMemOS comes in with this idea of a memory operating system. It's inspired by how human memory works, specifically enneagram theory, and it uses this three-phase life cycle.
To turn all those fragmented bits and pieces.
Right, those isolated little traces, and transform them into these coherent, really stable semantic structures.
And the payoff for all that work is what they call experience-grounded foresight. So the agent doesn't just recall a fact, it can reason about things over time.
Which is how you prevent those classic failures, like recommending a beer to someone who just told you they started taking antibiotics.
A mistake that current systems would absolutely make.
Oh, routinely. And the results really speak for themselves. EverMemOS just blows past the state-of-the-art baselines. Mem0, ZEP, the original memos.
What are the numbers on that?
Using GPT 4.1 mini, they got a 9.2% relative accuracy bump on the LoCoMo benchmark, which is huge, hitting over 93% accuracy. And on LongMemEval, they saw a 6.7% improvement.
Okay, so let's unpack that because we've seen this shift happening. LM agents are moving from being, a fun chat tool to something more like a long-term partner. But why does that jump require a whole operating system for memory? Why not just keep making the context window bigger and bigger?
Because the problem is fundamentally architectural. Long-term agents need to have a consistent persona, sure, but they also need to integrate constraints that change over time.
Like a diet or health goals or, a temporary medical issue. Things that last for days or months or even years.
And that's exactly where just having a bigger context window falls apart.
Even the massive million token ones.
Absolutely. For one, it's just incredibly expensive from a computational standpoint. But even if you could afford it, you run right into the lost in the middle problem.
Where the model just kind of forgets what's in the middle of a giant prompt.
Yep, it ignores crucial information. But the real technical issue is what the authors call the failure of fragmentation.
Which is that core idea we touched on, that older systems just treat memory like a flat list of stuff that happened.
Precisely. It's just a collection of isolated records. So your agent might pull up fact A, user loves IPAs, and fact B, user is on amoxicillin, but it has no mechanism to consolidate those into a rule.
A rule like current status, no alcohol.
It just can't see the conflict, which brings us right back to that IPA example. A fragmented system sees the strong long-term preference for IPAs, but it misses the temporary overriding constraint about the antibiotics, and boom, it makes a bad recommendation.
So EverMemOS is designed to fix that by moving memory from being like a flat file system to a structured, processed OS.
That's the core idea.
Okay, this is where it gets really interesting for me. Let's get into the nuts and bolts. Phase I is episodic trace formation, and it all starts with this atomic unit, the MemCell. What exactly is a MemCell?
A MemCell, which they call $6, is basically a structured tuple. You can think of it as a super rich log entry. It's way more than just a snippet of the conversation. It's formally DC equals E, E, F, P, and
Let's break those four pieces down because this structure is really the foundation for everything that follows.
Okay, so the first one is the episode, and this is key. It's not the raw chat history. It's a concise third-person narrative of what happened.
So the LLM actually rewrites the messy back and forth into a clean summary.
Exactly, which immediately gets rid of all the ambiguity and redundancy of a normal conversation. It's like turning chaotic meeting notes into a clean summary.
Got it. What's next?
Next is $5 for atomic facts. These are discrete, verifiable statements that are extracted from that episode, ALO. They're almost like database entries, designed for really precise matching during retrieval.
And then P for foresight. This feels like the game changer.
It really is the most novel piece. Foresight is all about forward-looking stuff, so temporary states, plans, important constraints. But the real innovation here is that each one is tagged with a validity interval, a start time and an end time.
That validity interval start seems critical. That's how the agent knows the difference between users on antibiotics forever versus users on antibiotics from Monday to Friday.
Exactly. Without that timestamp, the memory is static and, frankly, dangerous. This lets the system automatically know when a constraint has expired. The last piece, dollars, is just metadata timestamps, source pointers, that kind of thing.
So how does this all get created automatically? It sounds like a lot of work just to structure one piece of a conversation.
It's a three-step pipeline, and yeah, it uses an LLM to do the work. Step one is contextual segmentation. They have this thing called a semantic boundary detector that slides along the conversation.
It's looking for topic shifts.
Precisely. It's not based on time or sessions, it's based on semantics. When it detects a topic has wrapped up, it bundles those turns into a raw episode.
I noticed in the ablation studies that this LLM-based method beat fixed heuristics and even beat using the ground truth session breaks. That tells you that a memory is a thematic unit, not just a chunk of time.
That's a fantastic insight. Yeah, the ideal unit for memory is thematic. So once that raw episode is segmented, step two is narrative synthesis.
Where it gets rewritten into that clean third-person episode, ELL.
Yep. And then the final step is structural derivation, where another LLM prompt goes over that clean episode to pull out the atomic facts and the time-stamped foresight.
Okay, so phase I gives us these highly structured, temporally aware MemCells. Now for phase two, semantic consolidation. How do we go from these individual units to something like stable, long-term knowledge?
This is where that biological inspiration, the idea of systems consolidation, really comes into play. The system organizes these MemCells into a higher order structure called a MemScene.
So they're not just in a big pile, they're in thematic clusters.
Thematic clusters, exactly. And what's so important is that this happens online, dynamically, as new information comes in.
That sounds computationally heavy. How does it avoid having to recluster the entire memory bank every single time a new MemCell is created?
It's an incremental update. So when a new MemCell comes in, the system calculates its embedding and just compares it to the centroids of the nearest existing MemScenes.
Okay.
If the similarity is high enough, above a threshold, it just gets assimilated into that scene, and the scene summary gets a small update. If it's not similar enough to anything,
It just creates a new MemScene.
it just instantiates a new one. It's like adding a page to an existing chapter in a book or starting a whole new chapter. You don't rewrite the whole book.
I saw they tuned that threshold, Dodo, differently for the two benchmarks. It was 0.70 for LoCoMo, but 0.50 for LongMemEval. What does that tell you?
That likely reflects the nature of the data sets. A lower threshold for LongMemEval suggests the conversations in it are maybe a bit more sprawling, with looser thematic connections. So you need to be more generous to group things together. The higher threshold for LoCoMo suggests it's made of more tightly, cleanly clustered topics.
And this consolidation process then feeds the user profile, right?
It does. Instead of updating the main user profile with every noisy turn of dialogue, it uses these clean, aggregated scene summaries. This is how you separate the stable, long-term traits from the temporary facts, like a blood pressure reading that changes daily. It's constantly stabilizing the agent's model of the user.
Which brings us to phase 3, reconstructive recollection. The paper says the goal is necessity and sufficiency. How is this different from just standard RAG, which pulls up the top K similar documents?
Standard RAG is, at its heart, a static lookup. You search, you get a ranked list. EverMemOS treats retrieval as an active reconstruction process, kind of like how our own brains piece together a memory from different fragments.
So trying to build the perfect context for the task at hand, with no extra fluff.
Exactly, no fluff, and that's how it avoids the lost in the middle issue.
So how does it actually do that? How does it prune down what could be millions of memories?
It starts with MemScene selection. It uses a hybrid approach, fusing dense vector search with old-school BM25 keyword search over the atomic facts. They combine the scores using something called reciprocal rank fusion, or RRF.
It's like getting the best of both worlds, semantic and keyword search.
You got it. That process selects a small set of the top-scoring MemScenes, usually just 10 of them.
Wow, okay. So right there, you've gone from potentially thousands of individual memories down to just 10 thematic buckets. That's a huge reduction.
Massive. Then, from those 10 scenes, it moves to episode and foresight filtering. It pulls all the episodes from those scenes and re-ranks them to pick a compact set, maybe the top 10 episodes.
But the crucial part is the foresight filter.
Right. This is the magic step. It looks at all the foresight items, all those temporary constraints, and it only keeps the ones where the current time falls within that validity interval. All the expired stuff just gets thrown out automatically.
So the system knows the user was on antibiotics last week, but because today is outside that validity window, that constraint gets filtered out, and now it's safe to recommend an IPA.
That's precisely how it works. But there's one more layer, an agentic verification loop. After retrieving this context, another LLM acts as a verifier and asks a simple question. Do I have everything I need to answer this query accurately?
And if the answer is no?
If it's insufficient, and this happened for about a third of the questions on LoCoMo, it triggers a query rewriting step. It reformulates the search to find missing pieces. It's a self-correcting loop.
So the quantitative results clearly show this approach wins. But beyond the headline accuracy numbers, what really stands out to you in the data?
It's where the biggest improvements happened. The gains weren't uniform. The strongest relative jumps were on tasks that require exactly this kind of structured aggregation of knowledge over time.
You mean the really complex reasoning, not just simple fact lookups?
Exactly that. In LoCoMo, the multi-hop reasoning tasks, where you have to connect a bunch of different clues, shot up by almost 20%. Temporal tasks improved by over 16%.
And on LongMemEval.
The knowledge update tasks saw a massive 20.6% gain.
Which is direct proof that the MemScenes are working. They're successfully clustering related updates, letting the LLM resolve conflicts and figure out the current state of things, instead of just grabbing the most recent fact it saw.
And the ablation studies just hammer this point home. Take away the MemScenes and go back to a flat list of MemCells. Performance drops. Take away the structured MemCells and just retrieve from raw dialogue. Performance drops even more. It proves the value comes from that structured processing in phase on.
So what about efficiency? With all this LLM-based structuring and verifying, is it actually practical? Does the better retrieval make up for the upfront cost?
It does. They show this really nice accuracy-efficiency trade-off curve. Because that agentic verifier is so good at building just the right context, performance basically maxes out at around 10 retrieved MemScenes.
So it's not just grabbing more and more stuff, it finds what it needs and stops.
Right, which avoids noise and optimizes the final cost of reasoning.
Yeah.
It justifies the upfront investment in structuring the memory.
Let's talk qualitative. Beyond just being more accurate, what does this mean for the person interacting with the agent?
I mean, it leads to a much smarter, more personalized experience. The paper gives an example of tracking a user's waist circumference over time. Because it can see the trend, the downward trajectory, it sets goals consistent with that progress. It doesn't just give you some generic, useless advice like, aim for a healthy BMI.
And that foresight component lets it be proactive, not just reactive.
Absolutely. There's this great example where it warns a user planning a trip to Europe to book things in advance. Why? Because it retrieved a MemScene about a past trip to Beijing where the user was really frustrated because they missed out on things by not booking ahead.
So it learns from past negative experiences and applies that lesson to a future plan. That's incredible.
It really is. And the final piece is the user profile itself. Adding that consolidated profile boosted accuracy by over 9 points on a specialized benchmark. It just shows how that stable summary view provides this crucial context for high-level tasks.
So if we pull back and look at the big picture, EverMemOS seems like a real paradigm shift. We're not just thinking about LLM memory as a vector database you search anymore.
No, it's an active, self-organizing OS that processes and consolidates experience across a whole lifecycle. It's a fundamentally different way of thinking about memory.
Okay, so what does this mean for developers right now? The system's clearly powerful. What are the trade-offs? Where does the research go next?
The biggest trade-off right now is latency and cost. You have LLM calls to structure the memory in phase 1 and to verify retrieval in phase 3. That's just inherently more expensive than a simple single-pass system. The authors do mention you can cache things or run parts asynchronously to help with that, though.
And the benchmarks, as good as they are, don't really test the system over, say, 5 years of interaction.
That's the other thing. LoCoMo and LongMemEval are great for testing complex reasoning, but they don't yet stress test these ultra-long timelines the system is designed for. Developing those kinds of benchmarks is a huge area for future work. And of course, this is all text-based right now. Expanding to multimodal or embodied agents is the next frontier.
This makes me wonder, given how good the system is at handling temporal constraints with those MemCells and the foresight component, What's stopping us from using this to build agents that can plan really complex multi-step projects? Imagine an AI that could plan the construction of a building or a huge software project, while strictly following external rules and constraints that might literally change from day to day. That ability to track and filter what's true right now seems to be where the future of real agentic planning is headed.